Transformers changed AI. They powered GPT, Claude, Gemini, and almost every modern large language model. But they have a problem, a fundamental scaling problem, and it's quadratic. If you double the input length, you don't double the work. You quadruple it. What does quadratic even mean? When we say something is quadratic, we mean O square root of n. That means the work grows with the square of the input length. If 100 tokens, 10,000 interactions, 1,000 tokens, 1,000 million interactions, that escalates fast. But why? The real reason: self-attention. The core of a transformer is self-attention. Self-attention does something powerful. Every token looks at every other token. If you have n tokens, each token compares itself with n tokens. You get n times n comparisons, which becomes n times n equals square n. That's the quadratic explosion. What is being compared? Inside attention, each token generates a query vector, a key vector, a value vector. Then it computes similarity scores between every query and every key. So you form a full matrix of size, n times n. This matrix stores how strongly each token attends to every other token. That matrix alone becomes huge for long inputs. Why this gets expensive fast? Let's say 4,000 tokens turns into 16 million attention scores, 8,000 tokens turns into 64 million, 32,000 tokens turns into over 1 billion, and that's per layer. Modern LLMs have 30 to 100 plus layers, so the compute and memory explode. This is why long context models are expensive. Compute versus memory. Here's the key insight. Attention is not just compute heavy, it is memory heavy, because the entire n times n attention matrix must be stored during computation. On GPUs, memory bandwidth becomes the bottleneck, not raw compute. This is why optimizations like flash attention, KV cache, sliding window attention even exist. They are engineering solutions to this quadratic constraint. Why not just avoid quadratic attention? Because full attention gives us something powerful. Global context. Every token can see the beginning of the document, the end of the document, everything in between. That flexibility is what made transformers dominate. Quadratic attention is expensive, but expressive. The long context crisis. Now think about legal documents, research papers, code bases, 100K token context windows. If n grows, n squared grows brutally. For example, square 10n equals 100 times square n. Increase context length by 10 times. Cost increases 100 times. That's the scaling wall. This is the core constraint of LLM efficiency. Every optimization you'll see in this series is a response to this equation. Attention cost equals O square n. KV cache reduces recomputation. Flash attention reduces memory I/O. Pyramid attention reduces full resolution attention. Sparse attention reduces connections. Speculative decoding reduces wasted latency. But they all exist because of one thing: quadratic scaling. If you understand why transformers are quadratic, you understand the central engineering challenge of modern